Hi, myself Akshata Puri. My topic is calculation of bond energy, dissociation energy, and the resonance energy from the thermochemical. That now here I am going to discuss about the bond energy. Bond energy is defined as the amount of energy required to break a part of mole of molecules into its component atoms. It's a measure of the strength of a chemical bond. Bond energy is also known as the bond enthalpy or a bond strength. Then enthalpy of the reaction is equals to bond energy of the reactant minus bond energy of the product. Now here a problem on bond energy. The problem is like this. Estimate the average SF bond energy in SF6. The standard enthalpy of formation of SF6 gas gives as a sulfur gas and the fluorine gas are minus 1100, 275 and 80 kilojoule per mole respectively. The given data are the standard enthalpy of SF6 equals to minus 1100 kilojoule per mole. And hydrogenation enthalpy of sulfur equals to 275 kilojoule per mole. Hydrogenation enthalpy of fluorine equals to 80 kilojoule per mole. The reaction is like this. SF6 gas gives sulfur gas and the 6 mole of fluorine gas. And the formula of hydrogenation enthalpy of reaction is equals to the hydrogenation enthalpy of product minus hydrogenation enthalpy of the reactants. Products are sulfur and the fluorine and the reactants are SF6 gas. Here the hydrogenation enthalpy of sulfur equals to 275 and 6 mole of fluorine gas equals to 80 minus of hydrogenation enthalpy of SF6 equals to minus 1100. And the hydrogenation enthalpy of the reactants equals to 1855 kilojoule per mole. And we want the bond energy. The average SF bond energy is equals to the hydrogenation enthalpy of the reactants divided by number of bonds present in the molecule. Hydrogenation enthalpy of reactant is 1855 and the number of bonds 6 and the average bond energy is equals to 309.16 kilojoule per mole. Now we discuss about bond dissociation energy. The bond dissociation energy is the energy required in an endothermic process to break a bond and form two atomic or molecular fragments, each with one electron of the original shared pair. The bond dissociation energy is partially equal to the bond energy. Hence, the bond energy is the average dissociating energy of a given bond in a whole molecule. For example of this, H2, O2, N2 and etc. The bond dissociation energy is equal to the delta H is equals to 436 kilojoule per mole. Now we have a problem on this bond dissociation energy. Calculate the bond dissociation energy. The delta H for the reaction of methane CH4 gas with fluorine is minus 716 kilojoule. According to the equation, CH4 gas plus 2 mole of fluorine gas gives CF4 gas plus 2 mole of hydrogen gas. Use that information and the following bond dissociation energies to find the bond dissociation energy for FF in kilojoule per mole. Here they gives energies for CF bond 450 kilojoule per mole and CH bond energy is 410 kilojoule per mole and HH bond energy is equals to 436 kilojoule per mole. Now we have to find dissociation energy. The reaction is like this. Methane plus 2 mole of fluorine gives CF4 bond plus 2 mole of hydrogen. Now we break a CH4 bond, it gives a 4 mole of CH bonds. And we break a F2 bond, it gives 2 mole of FF bonds. We break CF4 bonds, it gives 4 mole of CF bonds. And we break H2 bonds, it gives 2 mole of HH bonds. We know the energies of these bonds. 4 mole of CH is equals to 4 into CH energy is 410 and this like this way the total energy is equals to minus 716 kilojoule. The reaction is CH4 plus 2F2 it gives CF4 plus 2H2. We know that this reactant value minus 1032 plus 2x, it gives minus 716. Now the value of x is equals to 158 kilojoule. The dissociation energy of FF bond is equals to 158 kilojoule. Now we discuss about resonance energy. The resonance energy of a compound is a measure of the extra stability of the conjugated system compared to the corresponding number of isolated double bonds. The resonance energy of a molecule can be estimated by comparing the enthalpy of change of hydrogenation. The amount of heat is released when the mole of an unsaturated compound is hydrogenated of the actual molecule and the canonical form of lowest energy. The resonance energy of a molecule is expressed in kilojoule per mole. The resonance energy is directly proportional to the stability of the molecule. So, the stability of the molecule increases with increasing its resonance energy. Now we have problem on resonance energy. Standard enthalpy of formation of liquid cyclohexane and benzene are minus 156 kilojoule per mole and 49 kilojoule per mole respectively. The standard enthalpy for hydrogenation of cyclohexane is minus 119 kilojoule per mole. Use the above data to estimate the resonance energy of benzene. We have to find a resonance energy. Solution: resonance energy is equals to energy of resonance hybrid minus energy of most stable structure. Then the theoretical value of enthalpy of hydrogenation of benzene or a cyclohexatriene minus actual value of enthalpy of hydrogenation of benzene or a resonance hybrid. We have enthalpy of hydrogenation of cyclohexane is minus 119 kilojoule per mole. Now the reaction is C6H10 plus H2, it gives C6H12. We know in cyclohexatriene there are 3 pi bonds. Then the theoretical value of enthalpy of hydrogenation of benzene is nothing but cyclohexatriene is equals to 3 into minus of 119 kilojoule. It gives minus 357 kilojoule per mole. It's nothing but X. Now consider the reaction. 6 mole of carbon plus 6 mole of hydrogen gas. It gives C6H12 of liquid. Then the enthalpy of formation of C6H12 is equals to minus 156 kilojoule per mole. Then 6 mole of carbon plus 3 mole of hydrogen gas, it gives C6H6 of liquid. Then the formation enthalpy of formation of C6H10 plus H2, it gives C6H12. We know in cyclohexatriene there are 3 pi bonds. Then the theoretical value of enthalpy of hydrogenation of benzene is nothing but cyclohexatriene is equals to 3 into minus of 119 kilojoule. It gives minus 357 kilojoule per mole. It's nothing but X. Now consider the reaction. 6 mole of carbon plus 6 mole of hydrogen gas. It gives C6H12 of liquid. Then the enthalpy of formation of C6H12 is equals to minus 156 kilojoule per mole. Then 6 mole of carbon plus 3 mole of hydrogen gas, it gives C6H6 of liquid. Then the formation enthalpy of formation of C6H6 is 49 kilojoule per mole. The reaction is C6H6 of liquid plus 3 mole of hydrogen gas, it gives C6H12 of liquid. This is the actual enthalpy of hydrogenation enthalpy of the benzene. Adding this reaction, it gives C6H6 of gas plus 3 mole of hydrogen gas. It gives C6H12 of liquid is equals to 205 kilojoule per mole. The enthalpy of hydrogenation enthalpy of benzene is equals to minus 205 kilojoule per mole. It's nothing but Y. Now we want resonance energy. Then we have to calculate resonance energy. Resonance energy is equals to the mm, actual theoretical value minus actual value. Theoretical value is nothing but x, and actual value is nothing but y. Theoretical value is minus 357 kilojoule per mole, and actual value is minus 205 kilojoule per mole. The resonance energy is equals to minus 357 of minus of 205 kilojoule per mole. Now the resonance energy is equals to 152 kilojoule per mole.